So we'll get started. I'm James Fairbanks, and this is Matthew Bespoke. And we're going to be talking today about graph interfaces, which is a way to build bespoke graph types for every occasion. And this is the summary of a lot of work we've done on LightGraphs over the last year. We've came around full circle. We started with LightGraphs thinking, well, there's this package called GraphJL, and it was like, you can make any type of graph you wanted, adjacency list, incidence matrix, adjacency matrix, anything you can think of. But it was really slow because this was like Julia 0.2, and the compiler wasn't that great. But it's gotten a lot better. And so we went from the simplest thing with no abstraction to now LightGraphs supports abstraction. Our third co-author is Seth Bromberger, and he was the rock that didn't want to adopt any abstraction, but we finally convinced him about last year's JuliaCon. Oh yeah. We'll also talk about the scope, show some code, and conclude at the end. There we go. Yeah, and as I said, we gave a LightGraphs talk last year that goes through detailed history. So the thing that we made LightGraphs transform into is both a base type defining kind of what is a graph. There's vertices and edges, and how do you interact with them? What's the interface look like? And then a suite of algorithms that we consider to be essential for anyone doing kind of applied graph theory. And that includes both, I was supposed to go down. I was supposed to go down here. That includes both kind of social network analysis stuff and logistics and operations research. I've focused mostly on social networks and internet networks, and Matthew has been doing a lot of OR stuff.
So if you found these applications boring, it might be the case. So we have some other more fun. So you can use graph to help Santa. So this is the Kaggle website, so offering data sets to help people train and solve big problems. So the first one is actually how I got started with LightGraphs. So this was a matching problem. You have a bunch of kids in the world, and you have a bunch of gifts, and you're trying to find the best match between gifts and children. And so I used LightGraph for this. Obviously, I was missing some syntax or some functionality, so I contacted them, and that's how I got started with the package.
Yep. And then also, once you've assigned the matching, you have to do traveling salesman problems so that Santa can get the gifts to the kids. Now I go over and this way. There's a reason PowerPoint is only one-dimensional. So things we've added, kind of, what is a graph? Well, it's a set with a set of vertices and a set of edges. And these are kind of the core interface you need to know. So you have to be able to get those edges, then some Julia stuff, like what's the edge type? Is this graph directed? How many edges does it have? How many vertices does it have? And then a set of those vertices. It's alphabetical order. Down again. So then these are kind of, so those are graph level operations. They work on the whole graph. Then you have vertex level operations, which work on a single vertex in that graph, such as computing neighborhoods. And then you have edge operations, which operate on single edges. So does this edge exist? What is the source? What's the destination? And how do I reverse that edge? And all of our graph algorithms are based on these primitives. So the core promise of LightGraphs is that if you implement these methods from these three slides, then any algorithm in LightGraphs will work. So you can generate, here we're showing simple graphs, kind of the default graph type, which is an adjacency, kind of an adjacency list. It's an array of arrays to encode the adjacency array. So you can generate a complete bipartite graph, and then you'll see here it kind of pretty prints, little description, and then ask for neighbors. Then you can do, okay, so I have a graph. What can I do with it? The first thing is to do shortest path calculations, like Dijkstra's algorithm. And here's a little wrinkle in our kind of Julia design that we really like, which is returning these structs like Dijkstra's state. Because when you're normally designing a graph API, you have to choose. When someone runs Dijkstra's algorithm, what do they want? Do they want the distances? Do they want the parents? Do they want the whole tree? How do they want it? And we use multiple dispatch and the lightweight structs to design our API so that you can efficiently store all of those things and calculate them on demand, depending on what the user finally wants. You can also do minimum spanning tree here, and then PageRank. So those kind of cover our social network and optimization and logistics kind of use cases. So then we try to play well with others in the Julia ecosystem. We think of JuliaGraphs as an ecosystem, just like the plots ecosystem or the optimization ecosystem or biology. And here's a way to do graph visualization. Then we can also do flows. So here, another big thing we worked on this year was kind of excising dependencies and externalizing them into other packages, such as all of our Julia opt dependencies kind of came out into this LightGraphs flows package. And matchings, I guess. So you can make a graph. Oh, we use abstract arrays for the capacities. So you can use any abstract array type for your matrix of capacities. Then you plot it. Then you solve the flow. And then you can plot the solution to the flow. So that's a really nice way, kind of we're crossing 3 ecosystems in 3 slides. And it's a beautiful piece of composability in the Julia language that we're able to hook all this up together. There we go. And so the promise is if you implement that interface, you get all the algorithms. And we have ways, to characterize and make things more efficient if your graph type needs that. And the rest is up to you. So anyone can build a custom graph type tailored to their need. Matthew's going to do the demo.
Okay, so we struggled a bit with the display, so I suppose some live coding is going to break. Otherwise, we deserve a beer at the end. Thanks. So what are we going to do? We're going to build the simplest possible graph. Like you want to play with the ecosystem. We don't like what we did. That's normal. So you want to build your own matrix for a graph. Why a matrix? Well, this is the simplest way to represent completely a graph. If you have a matrix of n by n entries, so you have n nodes, and if you have an edge from I to j, then you put a 1 in the matrix. Otherwise, you have a 0. Pretty simple. So this is all documented in the, this is all in the documentation, how you define from this matrix a complete graph for us. And, well, that's what we're going to try to do. So, so we have this interface. Is that a good one? Oh, no, it's not a good one. Yep. Come on. Yeah. So, yeah, there we are. So we're going to import some functions from LightGraphs, just like you would do from Base or from anything else when you want to redefine them for your own types. No pre-compiling if we're lucky. And then, so we're going to define our simplest possible graph, which is going to be just a matrix. In our case, a matrix of Boolean values, and we can use any type of matrix we want, so we just define it as abstract. So once you know what type of graph, what structure of graph you're going to have, you can use either a sparse matrix if you have a couple of edges and not more, or a dense matrix if you prefer, and so on. So yeah, hopefully, yeah. Oh, no precompile, we're lucky. So now, just like James said, we're going to define the basic methods we need on our graph. And what are that? We just need to know how many edges, how many nodes, what are the iteration over edges and over nodes. So that basic function you need to define. In our case, well, the first one is it directed? Well, we're just going to implement a simple directed graph. So we're always going to say yes when we are asking for this specific type. So for our matrix digraph. Then the edge type. So the edge type is just going to be the plain edge type already defined in LightGraph. We're not going to redefine it here. It's boring. Then the number of edges, as we said, is the number of entries in the matrix, which is non-zero, so 1. And the number of vertices is the dimension of the matrix. So this is a square matrix. We just need one of the 2 dimensions. And finally, the edges function returns an iterator. So what we need to do here is return any pair ij if the ij is equal to 1 in the matrix. So nothing fancy here. Anyone can do it from a matrix, and there we are. We almost have a graph. Well, then we need also, as we said, methods on the graph and a node. So how do we know the outer neighbors? Well, we just check for one row. What are the entries equal to 1? Same thing for the column. If you want the inner neighbors, so that means the nodes pointing to your node in the graph. And has vertex is simply, well, if I'm looking for a vertex I, is my matrix bigger or equal to I? And that's it. Yeah, so then methods and edges, nothing fancier. We just want to be able to query is one matrix has the edge. So it's basically checking at the entry ij, is it a 0 or a 1? Nothing more. And then what you can add is mutability. So this is optional. You can have mutable or immutable graphs. This is up to you. It's not mandatory in the interface. We just define it optionally. So if you want to define mutation for your graph, you can add edges, remove edges, add vertices, remove vertices, and so on. Okay, so now we've basically defined for LightGraph what our type is. So LightGraph can query anything on it, and well, we're gonna try a crash test. Yeah, that's a crash test in France. We just drink a bottle of wine and try some fireworks inside. So we're gonna try it on the SNAP dataset, which is a pretty well-known dataset from Stanford on graph research. Oops, too far. Yeah, so what we're gonna see now is, so we're gonna use the adjacency matrix, which is basically from any graph, give me the adjacency matrix of it, so ones and zeros. So nothing fancy here. And then we're gonna convert this basic matrix to our type, which is our matrix graph type, so that we defined above. And then, so we're gonna use PageRanks, which is a pretty well-known algorithm developed by, the founders of Google, so that's how they rank pages at the beginning. So nothing fancy here, we just use the basic function from LightGraph, which is, well, the basic PageRank. So this is pretty compute intensive if you have bigger graph, so that's how you know if your graph works or not. And that's the part which could break, we don't know. No, obviously not. So then we're gonna see what does our graph look like, and we're gonna use the ranks as the size of the nodes. So this, if you think in terms of the actual application of PageRank, this is how important a web page will be. So how many other pages will point to this page and so on. If it's willing to. Yeah, and well, spoiler, right? Yeah, perfect. So we see the 6th node is being pointed at by lots of other nodes, so it's considered as pretty important from its rank, and that's basically how Google used to work before. So we can do that on a bigger network if we're crazy and really want things to break. So we're gonna use another sample of a SNAP dataset, but a bit bigger this time. And so, just like before, we're taking this matrix from the data, we're converting it to our custom graph type, and then we're applying PageRank, so from the LightGraph library on it. Even though we did not define LightGraph for our type, it's already guaranteed because we respected the LightGraph interface. What we see here is, well, we don't see the importance of the nodes anymore, but what we see are different clusters of web pages, or even of nodes. So that means all these within a cluster, everyone's going to point to one another and so on, while between clusters, not many people have interests. So this is maybe the C and the Julia community. So in some cases, what could be interesting, so why not using the basic LightGraph types? Given your structure, you might know more, you might have more information than us about your graph type. So you have optional methods. You could use the default one, or you can re-implement it. So in our case, if we compute the adjacency matrix, what we're storing in our custom graph type is already the matrix. So we don't need to recompute all the edges. We can just give it back. So the default implementation is going to check all the edges and construct the matrix entry by entry. Well, what we can do here is just, well, hand over the matrix. So if we benchmark the initial computation, so the default implementation of LightGraph, we're going to have a pretty slow time, well, relatively slow time because we need to check all the entries, while in a custom implementation, which is just give it the matrix, it should be, so this is the first one, should be, and the second one. So the second one is obviously faster because we're just handing over matrix and converting the Boolean to an int to respect the interface. So if you have a graph type, you can just define the strictly needed methods, or if you know more, you can move a bit further and redefine the methods you know you're going to be more efficient for. So yeah, as a wrap-up, what you can do with LightGraphs is just define exactly what you need, so the very basic functions. If you want, you can define a bit more, depending on your use case and so on. But in any case, while you respect the interface, you're going to have all the battery included algorithms, and you're going to be able to rely on all the other packages from the ecosystem, including the plotting ecosystem. So you saw all the graph plot. We don't need to define anything for the plots of a graph. We just need to be a graph. That's it. Same thing for the optimization ecosystem. So we saw flow algorithms before. You don't need to define anything for that. Just be a graph and you're fine. So, and as a bonus here, so as a couple one-liners, you have a similar implementation, except we didn't want to have one implementation for directed graph and one implementation for non-directed graph. So you can just have it as an option. And with a couple more definitions, you have one type for both directed and non-directed graphs. And yeah, that's it.
Yeah. We're happy to take any questions.
First of all, great work. I've had a chance to try LightGraphs. I was wondering, there's a bunch of graph data sets over the web, and some of them are use the standard benchmarks for all sorts of click finding algorithms and etc. Do you have any plans to integrate these, or?
So the Snap datasets module you saw up there makes it easy to access that one repository of lots of graph datasets. Also, there's collections within Matrix Depot, which I know I've used in the past, and you can easily download something from Matrix Depot and bring it in.
Yeah.
But yeah, if anybody wants to write more connectors, I saw the data depths talk today. And it seems like that's a really good framework for building connectors between repositories of data and applications that use that data. So
The DMAX dataset would be quite useful, for example.
Which one?
The DMAX dataset, it's...
the Rutgers...
it's how people benchmark all sorts of graph algorithms.
Yep, that would be good as well. Yeah.
Fantastic.
So question here. In this examples, it seems just for the user perspective, it seems quite slow. I don't know if it's the gplot call. Is it the...
So just because you can represent a graph with a dense matrix doesn't mean you should represent a graph.
I mean, one of the calls that you had a calculating PageRank and then using gplot. What was the bottleneck there? Because that took like 2-3 seconds to run that
Yeah,
stuff.
I can answer on this. The heavy computation going on here is not the computation there. It's actually displaying from my laptop. I think I have some things broken there, so that's just it.
And a related question, why did you decide to, instead of overloading the plot function, why are you using a gplot function? What's the rationale for that?
That is historical. When we first started doing graph visualization, there was no standardized plot API. And then historical consistency.
Well, for that one, actually, it's because it's a user recipe in plots.jl. So it needs to be a user recipe for, there's some reasons why it needs to be that instead of specifically a type recipe, the way it has to deal with some of the arguments. And with the user recipe, you usually give it a different name because there's 4 different types of recipes. That's really the, yeah. But I have a question. So a lot of the times when you are dealing with graph algorithms, right, you're trying to choose the algorithm specifically not on a specific data type, but of traits about the data type that you have, right? You want to know something like
About the content rather than the
yeah, like is grabbing edge fast or is grabbing vertex fast, right? So do you guys have like a trait system set up with your PageRank algorithm such that it's able to query these kinds of details and do a fast path for as long as you've defined the traits, or is this?
Yeah, so we currently use simple traits, and the primary use case for that is for distinguishing between directed and undirected graphs. And you could see that you actually didn't have to do anything with traits when you're defining a new type. Yeah, that's as the new trait system comes out with 1.0, we're going to be adopting that on a go-forward basis.
All right, cool. Do you have an algorithm that I'm just kind of curious? Which algorithm would be the one to look at for like which it's auto specialize on details of graphs? Do you have one in mind?
Yeah. Thinking of things that are the place I'd go to is stuff like connected components. Right now uses a set of breadth first searches until you cover everything, but kind of parallel connected components algorithms kind of operate edgewise rather than neighborhood-wise. And so you could have a graph type where accessing like for all edges is faster than for all vertices, for all neighbors. So sometimes those are equivalent, and sometimes they diverge. Like in an edge list, for all edges is going to be faster than for all v, for all neighbors of v. So that would be the first place I'd go to, is distinguishing kind of, if you want to do updates fast, you might not sort the way we need to sort in order the current simple graph implementation.
Yeah, that sounds really cool. So I'm going to write that up for a GSLAC project. I'll put you down as the mentor, and hopefully we can see this in
Yeah.
there.
Do we have any other questions?
I was just curious, did you look at sort of the performance or runtime and compare it to other popular graphing libraries?
Yeah. So over the last 5 years or so, done quite a bit of benchmarking against other things. I'd say we're definitely faster than the other interpreted language, like dynamic language solutions, like NetworkX for sure. That's an easy one. Really, the place where I would say performance is not cutting edge is parallel and distributed. So when you get to the scales where you're kind of out of core, then we don't really support out of core right now. So if you're at that scale, that's where, but I think we're faster than everybody else as long as it fits in memory. That's the goal. If you find a benchmark where that's not true, just GitHub issue. We'll fix it. Well, great.